Alrighty, last video for this section, 3.5. So 3.5, it's different from the others. Actually, the math in it, in my opinion, is easier than 3.4. 3.4 was the peak, and now we're kind of dwindling our way back down. Anyway, there's Grumpy Cat. Oh, Grumpy Cat. Anyway, rational functions. So a rational function is when you have a polynomial divided by a polynomial. So everything we've been doing this section divided by another polynomial. They don't have to be the same. They can be different degrees. But whenever you have anything like that, that's called a polynomial. Or, sorry, a rational function. So proper and improper. So if we go back to just regular numbers, okay? So let's say 3/4 and 7/5. All right, we say that this one is proper and this one is improper. Now, do you remember why? This is way back in like 4th grade math. So a proper function means that the numerator is smaller. And they say that it's proper. Now, improper is if the, oh my god, really? Really? Okay, I'm gonna move this thing closer to me. I think my hand's hitting the zoom button. So if I bring it closer, I shouldn't hit. Okay, so smaller numerator. Improper means that it has a larger numerator. And when I say smaller, I mean smaller than the denominator. So 3 is smaller than 4, so it's proper. 7 is bigger than 5, so it's improper. Improper is kind of it makes it sound like it's bad, but in math, we actually prefer improper fractions. The only time we like proper is whenever we're dealing with measurements or you're answering a question, answering a word problem. But anyway, so here I'm going to go ahead and write two things out. Let's say I have x squared plus 1 over, fantastic, 1,250% zoom. All right. I like how I just did a video and it didn't do this at all, and now it's doing it. So no more touch. Okay. So x squared plus 1, x cubed, making something up. And then I have another one, and let's say this is x to the 4th minus 3x squared plus 7 over x squared minus 3x plus 2. Okay, so these are two rational functions. This one is proper. Whereas this one is improper. Can you tell why? They're completely, it's a different concept. They're not numbers. But it's the same idea. When we're dealing with rational functions, it's not the actual number itself, but it's the degree. Smaller degree on top. Okay? Here, notice that the larger degree is on top. So that's when we say we have a proper rational function versus an improper rational function. All right. So anyway, that's all it's saying. Improper if the degree of the top is less than the degree of the bottom. Improper if the degree on the top is greater than the degree on the bottom. So now we have lowest terms. So again, if I go to numbers and I write down, let's see, I'll write down 4, 6. And if I write this down, this is not in lowest terms. Why? Because we can simplify it. And you simplify it into 2/3, and then it becomes lowest terms. Okay? So anyway, with that idea, it's going to be the same thing. If I give you an equation, and again, I'm just making one up, x squared minus 9 over x plus 3, we would say that this is not in lowest terms because we can simplify it. If I simplify it, what we mean by that is you have to factor x plus 3, x minus 3, x plus 3, and notice that the plus 3's cancel out. And we're left with x minus 3, which this is the lowest terms. All right, so that's all that means. Lowest terms means that it can be simplified. Once you simplify it, then it's in lowest terms. Okay, so let's look at these examples. Write the following function in lowest terms only. So if I write this in lowest terms, all they want me to do is you know what, I'm going to pause the video and I'm going to see if I can move that because that's where all my issues are going on. Frustrating. Yeah, I think I got rid of them. Ha ha ha. Life is good again. Okay. So, what they want us to do to put it in lowest terms is we have to try to simplify. And by simplifying, we have to try to factor. So, x squared minus 16 simplifies to x plus 4, x minus 4. These cancel out. Now, before I do anything, I guess it didn't work because it just did the same thing again. That is very, very frustrating. Okay, so these cancel. And notice that there's still a 1 on top, and you have 1 over x minus 4. And now we have our lowest terms. So let's go to the next one. This one's a bit more complicated, but we're just going to try to factor. Now here we're looking for two numbers that multiply. I'll go ahead and write it down here. For the top, two numbers that multiply to negative 21, but add to 4. So what two numbers do that? And it turns out that they're positive 7 and negative 3. Because that's negative 21, whereas plus 7 minus 3 is 4. So because those are those two numbers, this means this is x plus 7, x minus 3. Now I can do the same thing. For the bottom, I want two numbers that multiply to 28, but add to 11. And so let's see, that's going to be 7 plus 4. Positive for both of them. And because 7 plus 4 gives me 11. So here it's going to be x plus 7, x plus 4. And there you go. These cancel. And then we have x minus 3 over x plus 4. All right. Now, this is again lowest terms. All right. Now, just for a quick refresher here, we talked about this way in the beginning of exam 2. But when you're looking for the domain of this, just in case some of the homework questions ask you for the domain, all right, you always use the original problem, not the simplified problem. Because I didn't give you 1 over x minus 4. I really gave you this problem, which doesn't exist if we have 4 or negative 4 in the denominator. So for the domain, you use the original problem. All right, and the original problem was everything but 4 and negative 4. So the domain is negative infinity to negative 4 union negative 4 to 4 union 4 to infinity. Now again, that raises the question, well, looking at my final answer, I can tell that this 4 here is going to be a vertical asymptote. Let's go to Desmos so I can show you. Desmos. All right. So in Desmos, I type in, I forgot what the numerator was, x plus 4 over x squared minus 16. And there's our graph. Right? And notice that at x equals 4, we have a vertical asymptote. Okay? But the question is, if you look at the domain though, and if we're using the domain of the original problem, the 4 is the vertical asymptote. What happens at negative 4? Notice that the function can't be negative 4 because the original problem can't be negative 4. Negative 4 squared is 16. 16 minus 16 is 0. So if I go back to my graph, if you look at negative 4, it looks like you don't see anything wrong there. It looks like everything is happy and nice. But it turns out if you go slowly, oh, there it is, undefined. There is nothing there. So even though it's simplified and it went away in the final answer, it's still not there, but it's not a vertical asymptote. It's actually a hole. And so this is going to be 4, negative 4, sorry. And, okay, negative 1/8. I'll explain how I'm getting this number in a bit. And so what that is we have a hole. So a vertical asymptote at 4 and a hole at negative 4. Right? Same thing over here. If I move on to this problem, the domain for this problem is the domain of the original problem. So everything but negative 7 and negative 4. Right out of room. Anyway, that's just if the homework asks you for the domain. Just remember to always use the original problem and not the simplified answer. All right, next page. Vertical asymptote, like I mentioned before, or not like I mentioned before, but a vertical asymptote is basically a vertical line that the graph can't cross. So here's an example of a vertical asymptote. The graph does everything it can to avoid it. Right? So that vertical asymptote means it's what happens when you divide by 0. What could happen, not really what happens. Remember, there's holes too. when you divide by 0. Okay? And notice what's happening is the graph is pretty much doing everything it can to avoid the line, because you cannot divide by 0. So the graph's moving, and then it avoids it like the plague. It can't touch it. But it gets infinitely close to it. The farther you go down, the closer it's going to get. I'm so used to my regular tools that. Anyway, so the more you go down, the more you go down, the more you go down, the closer it gets. But let me go back up. Get everything centered. Now from the other side, the same thing. It's going, but then it avoids the graph, and it starts going on forever. So as you get close to an asymptote, the graph can either go do two things. The graph can either go up forever, or it can go down forever. Here it goes up forever. Here it goes down forever. Okay. Cool. Now let me see if I can try to clear the screen. Right, but it doesn't always look like this. I can change the way it looks. So notice on the right it went up, and on the left it went down. But all I got to do is put a negative in front of this thing, and it switches. Now the left side's going up and the right side's going down. Okay, so it doesn't always look the same, but it either always goes up or always goes down. Now on the bottom, if I squared it, this is probably not going to have the effect that I want. Yeah, there you go. So notice that it's going up on both sides, so that could happen. And I just put a negative in front of that, and it can go down on both sides. So those are the behaviors of the asymptote. You can either go down on both sides, up on both sides, get rid of that squared. It can flip-flop like that, or if you put a negative in front, it can flip-flop the other way. Those are the different shapes. Anyway, going back over here, that's what an asymptote is. Now, how to find them without using your calculator. So to find them, it's pretty simple. First, you have to make sure that your graph's in lowest terms. Lowest terms means that you have to simplify. Once you simplify, then your fraction's going to look like you're going to have your numerator and your denominator, and any real zeros of the numerator all you're going to do is numerator equals 0, is solve that. That's going to give you, actually I lied to you. That's the x-intercepts. Now for the denominator, you set that equal to 0. And if you go ahead and solve that, that's going to give you your vertical asymptotes. Right? And it always works like that. The one thing you got to remember, though, is you have to simplify first. Okay, so you have to cancel it. If anything cancels out, you cancel it out first, and then you set the top equal to 0 and the bottom equal to 0. The top gives you your x-intercepts. The bottom gives you your vertical asymptotes. All right, so let's look at these two. Find the domain, x-intercepts, vertical asymptotes for the following rational functions. All right. So we have 2x minus 7 over x squared minus 81. And so the first thing we try to do is we try to simplify. X squared minus 81 is x plus 9, x minus 9. One thing to note here is that nothing cancels. Okay. Now, right off the bat, I can figure out what the domain is. The domain is where the denominator is 0, so everything but negative 9 and 9. So the domain is negative infinity to negative 9, negative 9 to 9, 9 to infinity. Okay, so numerator equals 0 are your x-intercepts. Two x minus 7 equals 0. Add 7, divide by 2, x equals 7 halves. So as a point, as a coordinate, it would be 7 halves, 0. Now vertical asymptotes. We have the denominator equals 0. And that's just x plus 9, x minus 9 equals 0. And so we have our two solutions. You have x plus 9 equals 0, and x minus 9 equals 0. So x equals negative 9, and x equals positive 9. Now these are not points. These are vertical asymptotes. And so when your vertical asymptotes are there, they must have the x equals. Or it's incorrect. Usually on the homework, the x equals might be written in there for you. Like it'll say x equals blank, and then you just type in the number. But if it's just a blank with no x equals, and they want the vertical asymptote, you have to put the x equals. You'll be wrong, and then you'll email me saying, why is it wrong? Because the vertical asymptote is an equation, it's not a number. Anyway, and I think is that all they asked of us? Domain, x-intercept, vertical asymptotes. So let's go to Desmos, and let's graph it, and show that everything we did is correct. So we get 7. And then divided by x squared minus 81. Okay, so we said that our intercept was at the point number 2. 0. That's right, that's your intercept. Yeah. The vertical asymptotes were at x equals 9. And the other one was at x equals negative 9. Okay. So all you're doing is you're figuring out all this information without graphing it. I'm graphing it to show you that it worked, but you can find all this information without graphing it. Okay? And that's the whole point of this section. All right. So now let's go to this nasty looking one. Gross. So I have 5x cubed minus 15x squared minus 50x over x squared minus 8x plus 15. So my first thing is I'm going to try to factor. Notice that on the top they all have 5x in common, which leaves me with x squared minus 3x minus 10. Okay, on the bottom, I'm just going to leave it as is for a bit. So now what we're going to do is we're going to factor each of these. So two numbers that multiply to negative 10 but add to negative 3 is negative 5, so write the 5x, negative 5 and positive 2. Two numbers that multiply to 15 but add to negative 8 is negative 5 and negative 3. Notice the x minus 5's cancel. Okay, so now let's answer the questions. For the domain, always use the original problem before you canceled anything out. So for the domain, yeah, it was a weird sound. For the domain, it's everything but 5 and 3. So, because that's my denominator. So negative infinity to 3, 3 to 5, 5 to infinity. Okay? If you use just the last answer, all you're going to get is the 3, and you're going to be wrong. So not only is it the 3, but you go to the thing that you canceled out too, and that's going to be a 5. Visually speaking, this is my vertical asymptote, and this is my hole. Okay, now we can find the x-intercepts. The x-intercepts are just numerator of the simplified equation equals 0. So we have 5x times x plus 2 equals 0. And that spreads out into two solutions. You have 5x equals 0, and x plus 2 equals 0. So x equals 0, and x equals negative 2. So we have two x-intercepts. For the vertical asymptote, you just do denominator equals 0. And so my denominator of the simplified equation is x minus 3. So it's just x minus 3 equals 0. So x equals 3. Here, the vertical asymptote, that's the answer. For these are coordinates. So if you wanted to write the coordinates for the x-intercepts, it would be 0, 0, and negative 2, 0. Yay! So hopefully if you have any questions about that, let me know. But for the sake of funness, let's go ahead and graph it. 5x cubed minus 15x squared minus 50x. So 5x cubed minus 50x squared. Okay. And that's 50x. Yep. X squared minus 8x plus 15. Okay, x squared minus 8x plus 15. Trying to see where the other one goes. There's a middle part, but I guess it's so deep down you can't see it. All right, so we have this graph. I'm going to try to change the axis so it doesn't look so crazy. Oh yeah, there's both asymptotes. Okay, so hold on, I need to fix something. This is just a bad day. All right, I'm already too far in to stop. But what I messed up is I put 50 twice because I can't apparently see. So anyway, my x-intercepts were 0, negative 2. There they are. And I had one vertical asymptote at x equals 3. And there you go. Yay. So that's what the math is allowing us to do. We find the x-intercepts, we can find the vertical asymptote. And for the domain, remember that there was nothing at 3 or 5. So if I go to 5, it should say undefined. There it is. All right, anyway, next page. So now we go to the wholes. This is what I've been kind of talking about, but I never really told you how to find them. Okay? So anything that cancels out, basically stuff that cancels, you set it equal to 0 and you solve. That's how you find the whole, the x value of the whole. Okay? Whatever canceled out, set it equal to 0. That's your x value. To find the y value, you plug it into the simplified equation. That's it. All right? So for the last equation that we did, the x minus 5 canceled out. So the last problem, x minus 5 canceled. So that means you set x minus 5 equal to 0. So x equals 5. Now to find the y value, you plug the 5 into the simplified equation. And the simplified equation was up here, 5x, x plus 2, x minus 3. And so we plug the 5 into there. Make sure I got it right, because apparently today is a bad day with me misreading stuff. 5 blank x plus 2, x minus 3. Yeah. Right, and so when you work that out, you get 25 times 25 times 7. So 4, 5, 6, 7. That's 175. 5 over 3 is 2. So that's the y value. So that means that you have a hole at the point 5, 175 over 2. So if I go back to Desmos, I can find that hole by typing in 5. Oh my god. 5, 175. I'm having to reach over my laptop to type. It's frustrating. Anyway, so there you go. Now that value would be a hole. And so that's your completed graph. There is a little empty space right there. All right. Okay, horizontal asymptote. So the definition of a horizontal asymptote is just, let me go back to Desmos, it's just a number, the same as a vertical, it's just now it's horizontal. So horizontal asymptote is going to make up something really happy. Let's say 1 over x plus 2. Yeah, you know what? Oh. I put equals. I can't even see. First presentation ever. Anyway, in this case, y equals -2. But we would call it a horizontal asymptote. The graph never gets there. It just gets really close. Okay? So that's the idea of a horizontal asymptote. The same thing as a vertical, just on its side. Now, what's different about a horizontal versus a vertical is that the graph, I'm just going to put the keyboard in front of me, enough of this awkward typing, is that the graph is actually allowed to cross. So I'm going to show you another picture. Let's say I have 5x cubed over x squared minus 4 Hold on. Oh, God. All right, I went and cried for a bit. Anyway, we're back. And I wanted to show you this example because we have a horizontal asymptote. Stop it. And notice that it actually crosses. It is legal to cross a horizontal asymptote. You can't cross a vertical, but you can cross a horizontal. Okay, so that's basically the big idea here is that the graph can cross a horizontal. Okay, so how to find them? Really, there's a calculus definition for how to find them, but since this is college algebra, we just give you basically what you need to know in order to get it. And the real reason is whenever you have a rational function, so you have your top over your bottom, let me write it this way. You have a larger degree and you have a smaller degree. Whenever you divide the two, again with long division, like we did in the last 2 sections ago? Yeah, 2 sections ago. It's the quotient plus the remainder over the denominator. And it turns out that this quotient is what the graph looks like. And we talked about that last week. So if the quotient happens to be a horizontal line, then the graph's going to look like a horizontal line. We have a horizontal asymptote. So basically, these are 3 scenarios where the quotient is a horizontal line. And let's go over the 3. So let's start with this one down here. I don't know why I put that top one as the other one. Oh, okay. So if the degree of the top is larger, then there is no horizontal asymptote. Okay. So if the degree of the top is larger, then the quotient is going to have an x in it. And if the equation has an x in it, then it's not horizontal. But there's a special case where it could be slanted. So if you're dealing with your, I'm just going to write it. So we got the denominator. And if the top is 1 degree more than the denominator, okay, then we have what we call a slant asymptote. Okay, and all the slant asymptote is the quotient whenever you do your synthetic division or long division. In our class, we don't deal with it that much. I'm going to show you one example where it happens. Anyway, second and third bullets. If the degrees are the same, okay, then the asymptote is just y equals a over b, where a and b are the leading coefficients of the top and the bottom. So again, I'm going to use these examples below to show that. Now the easy one is if the degree on the top is smaller, then it's just y equals 0. There's no math. So for the horizontal asymptote, usually there's no math needed. You look at your equation. If the top is smaller, y equals 0 is the horizontal asymptote. If the degree of the top are the same, then it's just the numbers, the leading coefficients, a over b. If the top is larger, there's no horizontal asymptote. But if it's one more, we have what's called a slant asymptote. So I know that I'm kind of butchering this right now, but let's go over some examples and hopefully it'll clear things up. So this first example, I put dot dot dots because it does, when you're dealing with horizontal asymptotes, the other terms don't matter. All you care about is the first terms. And so if I look at this, I have a degree 2. And here I have a degree 4. Okay? This means that the top is smaller. So looking at the rules, if the top is smaller, y equals 0. So my horizontal asymptote is y equals 0. Remember, you don't just say 0, you have to say y equals 0, or it's wrong. I look at this next one, and notice that we have degree 3. We have degree 3. Okay? This means that degrees are the same. Well, if the degrees are the same, all you do is you take the leading coefficients and you divide them. The leading coefficients are just this number and that number. So my horizontal asymptote is just y equals 3/7. So hopefully this is clearing things up. I know I was getting convoluted over there. I go to the next one. Notice here I have degree 2. Here the exponent is a 1, degree 1. And we would say that the top has a larger degree, but only by 1 more. Okay? So if that's the case, then first of all, there's no horizontal asymptote. Because the top is larger. That's what this rule up here was saying that I was trying to explain and kind of butchered it. If the degree of the top is larger, no horizontal asymptote. Okay? But since it's only 1 more larger, we can actually do synthetic division. So in this case, this would be 7. Remember that since the denominator is blah, 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 or I'll write it out. 3x squared minus 2x plus 5 over x minus 7. Remember that the minus has to be in the formula. It's the number next to the minus sign. That's the c. So we have 7, and then 3, negative 2, 5. So if I do synthetic division, 7 times 3 is 21. Negative 2 plus 21 is 19. And that's some huge number. I don't really care what these are. But what I do care about is that. So we have what's called a slant asymptote. And the slant asymptote is the quotient. That's what I was trying to talk about earlier, which is y equals 3x plus 19. Okay, it's not a horizontal asymptote. It's a slant asymptote. And again, that only occurs when the degree on the top is 1 more than the degree on the bottom. Okay, you divide, and you end up getting your answer. Right, now we go to the last one. This is degree 5. This is degree 2. The top is now larger, by more than 1. And so we just say no horizontal asymptote, and that's all you got to do. Okay, So the only time you got to do special work if it's larger is if it's just one larger. So these are the four possibilities you're going to see. If the top is smaller, y equals 0. If they're the same, you divide the leading coefficients. Okay, if the top is larger by 1, then you go ahead and divide. Sometimes you won't be able to do synthetic division. Sometimes you have to do long division. But you divide, and whenever you're done, your quotient is the slant asymptote. If it's by more than 1, then there's just none. So let's go to the next page, and let's do some examples. So if I was giving the test, like had this pandemic not been going on, and I would give you the test in person, this is what the questions would have looked like. You would have had your equation, and then had to find all the values, basically just fill in the table. So let's go ahead and do it. But these are good practice for your homework. Your homework's not going to ask you to find all of them, but it might give you the equation and say, find the x-intercepts, or what's the horizontal asymptote, or what's the whole. So this gives you practice solving all of them. So our first task is going to be to try to simplify this thing. So we have 2, I can factor 2 out of the top, and on the bottom, I can factor that into, okay, hold on, let me adjust my clock here. All right, so that is x plus 5, x plus 2, because 5 plus 2 is 7, 5 times 2 is 10. I can keep on going. This is x plus 2, x minus 2, x plus 5, x plus 2. Oh my god, I'm going crazy. The x plus 2's cancel. And so now I'm left with 2 x plus 2 over x plus 5. So this is the simplify part. So now that we got that, I can answer every single question here. So let's start with the whole. Okay, so basically we asked ourselves what canceled. All right, well, what canceled was x plus 2. You set that equal to 0. So therefore x equals negative 2. Now to find the y value, you plug it into the simplified equation. So we end up with 2 blank plus 2 over blank plus 5. And you get your answer, the negative 2, and you plug it in. So that gives negative 2 plus 2 is 0. 0 times 2 is 0. Negative 2 plus 5 is 3. So 0. So my whole is at negative 2, 0. Let's see. Oh, I can't win today. I just can't. It's not happening. I'm making like every little mistake I can possibly make. The minus 2 is the one that stayed. Anyway, so I have 2, negative 2 minus 2, negative 2 plus 5. So negative 4 times 2 is negative 8. Negative 2 plus 5 is 3, so negative 8 thirds. So my whole is at negative 2, negative 8 thirds. So I got my x value and I got my y value. All right, so for x-intercepts, I gave my, yeah, okay. So for x-intercepts, it's just the numerator equals 0. But the numerator of the simplified form. So 2x minus 2 equals 0. That 2 doesn't do anything. It's just 2 equals 0, which doesn't make any sense. But this other one is x minus 2 equals 0. x equals 2. Right? And so I have one x-intercept, and that's going to be at the point, at the coordinate 2, 0. Remember, this is also a point. Now, a vertical asymptote is just the denominator equals 0. The denominator is x plus 5. So x equals negative 5. Remember, you have to have the x equals or it's incorrect. Got to have the whole thing. And then finally, the last one, horizontal or slant. So what I'm doing here for this one is, and you can use whichever one you want. This is 2x minus 4 over x plus 5. Now, if you use the last answer, notice that you have degree 1 over degree 1. If you use the original, you have degree 2 over degree 2. So it doesn't matter which one you use. But pick one, and the answer is going to be the same. So they're the same degree. And so your answer is going to be y equals, and then you divide the leading coefficients. So my leading coefficients were 2, and the number in front of x is 1. 2, number in front of x is 1. So the answer is 2 over 1, which I can just write as 2. There you go. Okay, so I apologize for the screw up in the beginning. I really wish I was in class so you could catch the little mistakes that I've been making. Anyway, next page, or this example. All right, so this equation is x cubed plus 2x minus x minus 2 over x squared minus 4. Now this one is a little different. I picked it because I wanted to have a slant asymptote. So first, let's try to factor it. The top is special. X cubed plus 2x squared minus x minus 2. This is a cubic, and any cubic I give you in this section will be factorable. And we do it by factor by grouping. So these have an x squared in common, which leaves us with x plus 2. Those others have a negative 1 in common, which leaves us with x plus 2. And again, you still have your two groups. That's group 1. That's group 2. But then you ask yourself, what do they have in common? The x plus 2. So x plus 2, x squared minus 1. And then finally, x squared minus 1 factors into x plus 1, x minus 1. So that one was a little tricky, but I can rewrite that up here. I don't want x plus 2, x plus 1, x minus 1. And on the bottom, I just have x plus 2, x minus 2. So notice that the x plus 2's cancel, which leaves me with x plus 1, x minus 1 over x minus 2. So let's go ahead and fill all this in. I'm going to write the work that I did for this problem. I'm going to shrink it and shimmy it to the right side so I can have some room for myself. So for my whole, we ask ourselves what canceled? Well, what canceled was the x plus 2. So that means x equals negative 2 is the x value of the whole. Now the y value of the whole is you plug it into the simplified equation. So my simplified equation is blank plus 1 blank minus 1 over blank minus 2. And so I just plug in my -2 into all those. And so that gives me, oh god, 1. Oh my god. -1, -3, -4. So that gives me -3/4. So we found the whole. All right, x-intercepts. X-intercepts are just numerator equals 0. So my numerator is just x plus 1, x minus 1 equals 0. I don't know why I wrote that on the bottom so big. And so if you solve each of these, they're easy to solve. You get your two solutions, x equals -1 and x equals 1. So my x-intercepts are at -1, 0. Remember, the x-intercepts are points. And it's -1, 0, 1, 0. Vertical asymptote is your denominator. My denominator is x minus 2 equals 0, so x equals 2. And now I find the horizontal or slant asymptote. Now in this case, I'm going to use the simplified version. Just rewriting it here to help me out. If I were to FOIL that, that's x squared plus 0x minus 1. So I just put that 0 in the middle. And notice that on the top, it's degree 2. On the bottom, it's degree 1. So that means that the top is bigger by 1 degree. So that means that we can, in this case, do synthetic division. If I do synthetic division, I have 2. The numerator, the coefficients are 1, 0, -1. 2, 2, 2 times 2 is 4, 3. And all I care about is the quotient. So here, the quotient tells me x plus 2. Y equals x plus 2 is my slant asymptote. All right. So yeah, that's for as far as slant asymptotes go, that's going to be the hardest they get. Everything in this section is factorable. You won't have to do the quadratic formula unless you don't want to factor. Let's go to the next page. All right. So what they want you to do after they figure out how to find it is they're trying to get you to graph it by hand. So basically this next example, and then we get to some word problems, is just how to graph it by hand. It's a little tedious, and doing this online is kind of different because you have pictures and it just says pick the right picture, and that doesn't really do it justice. But let's do this one example. And yeah. So first we have the definition of a critical number. This is a definition that you're going to see a lot in calculus. A critical number is just a fancy way of saying important x values. Okay. What do we mean by an important x value? What makes an x value important? Well, it's important if it's an x-intercept. Because remember, x-intercepts are factors, so that's important. It's important if there's a hole. If the graph doesn't exist, I want to know about it. And then finally, it doesn't exist if it's a critical number if it's a vertical asymptote. So those are what we call critical numbers. X-intercepts, holes, and vertical asymptotes. And again, when you get a calculus, you're going to spend a lot of time finding x-intercepts, holes, and vertical asymptotes. But anyway, so here's just a bunch of steps. And it seems really that in the book they give you 8 steps to do it. But if you look at the last 2 examples, Those last two examples we did were basically steps 1 all the way to 5. Okay? So it's just steps 1 through 5 are just find information. Factor the numerator, denominator, cancel anything out, which means find the holes, locate the x-intercepts, locate the vertical asymptotes, find the horizontal asymptote. So that's stuff that we kind of already went over. 6 is optional. I'm not going to do it. But if you want, you can test for even or odd. But we already covered that in exam 1, so I'm not going to retest over it. Gilbert's going crazy. So for now, I'm going to cross that off. 7, create a number line with tick marks. So this is the new part. Basically, the only new part this whole entire page is adding is step 7. So what they want you to do is they want you to find your critical numbers, and all your critical numbers you make tick marks. So you have a number line. A tick mark is an actual line that goes through it. Okay? So here's the example below. I have my x-intercept as a tick mark, I have a hole as a tick mark, and I have a vertical asymptote as a tick mark. And all they want you to do is pick values in each region. So in this little example, notice that there's a region here, there's a region here, there's a region here. So the critical numbers split your graph into regions. And all they want you to do is pick an x value in each region. And it says it up there too. It doesn't matter where. And find its y value. So this is the only new step that we're doing. And so again, here there's 4 regions, so the little dots show the numbers that you picked. They don't have to be in the middle. As long as it's anywhere within the region, it's good. And you pick your points, you plug them in, and you find their y values. So on this page, this next example, I'm going to go through that whole process. And that step 7, the new step, is part C, and I'm going to go into detail when we get there. So first, let's go through steps 1 through 5, which is basically just filling in this table. So again, this is steps 1 through 5. So here I have my equation. I try to factor it. The top has 3x in common, which leaves us with x minus 4. On the bottom, you can factor that. 2 numbers that multiply to 8 but add to negative 6 are negative 4 and negative 2. Notice the negative 4's cancel. So you're left with 3x over x minus 2. And I'm paranoid right now. Is my video even still recording? Because last time it cut off early. Yep, still recording. All is well in the world. Okay. So we have 3x over x minus 2. So first I'm going to find the hole. So my hole is what canceled out. So that's the x minus 4. So x is equal to 4. So my hole is a point. And the point is 4, comma. And in order to find the y value, you plug the 4 into the simplified equation. It's been a long night. I'm just falling apart. So this gives us 12 over 2, which is 6. So my hole is at 4, 6. I'll write down words here. Plug into simplified equation. All right, so the x-intercepts, it's just the numerator equals 0. Well, that's just 3x equals 0. And that's really easy to solve. That's just x equals 0. So as a point, it's just 0, 0. I'm not going to make you find the y-intercepts in this section. So here, think of this as x-intercepts. I forgot I changed it from when I was at my other school. Okay, vertical asymptote is the denominator equals 0. So that's just x equals 2. And then the horizontal or slant asymptote, well, if I look at my equation, notice that they have the same degree. Since they have the same degree, you just say y equals, and then you divide the leading coefficients. The coefficient of the top is 3, the coefficient of the bottom is 1, and so that's just 3. Okay. Now I'm going to erase the 3 over 1. It just looks weird writing it like that. But we end up with just y equals 3. There you go. So steps 1 through 5 of this whole process are done. Cuckoo. And now we're going to go and ask ourselves this question. Remember that it's possible to cross a horizontal asymptote. So since it's possible, we ask the question, well, does it? So in order to figure that out, all you got to do is you get your equation and you set it equal to whatever the horizontal asymptote is. And I should say further your simplified equation. Oh my God. So my simplified equation was just 3x over x minus 2. And my horizontal asymptote, if I go back to it, was 3. And so we solved that equation. If you get an answer, it means that yes, it does cross. If you don't get an answer, it means that it doesn't cross. So we get 3x equals 3x minus 6. And notice that we get no solution. You subtract 3x from both sides, and you have 0 equals negative 6. So what this means is that this is false, which means that this guy is false from our equation. So no, it doesn't cross. So when we're actually creating our sketch, we know that it's never going to cross the horizontal asymptote. All right, so now comes that part C thing, the tick mark thing that I was talking about earlier. So we have to create basically a list of numbers to help us make our graph. So first, we're going to write our critical numbers, our important x values, I should say. So my important x values were my x-intercept, my hole, my vertical asymptote. Okay. Looking back, the x-intercept was 0, the hole was 4, and the vertical asymptote was 2. Okay. So what step 7 wants you to do is it wants you to make a number line. And it wants you to make those three numbers that you just found tick marks. I'm going to put them in order. So 0 goes here, then 2, then 4. Okay, and if you want, you can label what each one is. Okay, so this splits our number line into 4 regions. Okay, what we're going to do is pick a number in each region. And put it in the table. That's it. So you can pick any point you want in each region. It does not matter. What the points I pick are just the easiest point I can think of. -1, 1, 3, and let's say 5. So I'm just going to get those points, and I'm going to put them here. -1, 1, 3, 5. Now all I got to do is find the y values. So my equation is just 3x over x minus 2. So 3 over minus 2. Here, if you had a calculator, you could just type it in your calculator. And so my numbers are -1, 1, 3, and 5. So this is -3 over -3, which the answer to this gives me 1. So that's going to be the answer over here. 3 over -1 gives me -3. So that's going to be what goes over here. 9 over 1, this gives me 9. And then finally 5, 15 over 3. 15 over 3 is 5. And so that's going to give me a 5. There you go. So that's all step 7 is. You make a number line with tick marks, and you pick any number you want in each region and make a table of values with them. Okay? The table of values is the numbers in between. It's not the tick marks. Anyway, so now that I have all that, I put it all together to create my graph. Whew. So let's do it. Let's start with the vertical asymptotes. My vertical asymptote is 2. My horizontal asymptote is 3. So here I have 2. Okay, that's x equals 2. Now y equals 3 is over here. Right? We know the x-intercept. So my x-intercept was 0, 0. And I know that there's a hole at the point 4, 6. So this is why we need that extra step. Because without that extra step, this is all we have. Steps 1 through 5 just give me the asymptotes, x-intercept, and the hole. And notice that that's not really enough to create a good graph. So that's the whole purpose of part C. So why are we doing this? To find extra points to help us graph. All right, so let's graph them. The points were -1, 1, 1, -3, 3, 9, and 5, 5. And we know that it doesn't cross. So that means that the graph is going to be in this upper right region and in the lower right region, and it doesn't cross in any way. So what the graph's going to do is it actually does this. Remember that you can't touch a vertical asymptote. And then it approaches the other asymptote, but it doesn't touch it. Same thing on the other side. So if you start at the x-intercept, I know it has to go toward the asymptote, going through that point, so it's going to get closer and closer and closer, but it's never going to touch it. Same thing here. It gets closer. The asymptotes act like magnets. The graph wants to get closer. It's just that it never actually gets there. And there you go. That's your graph. On the homework, they're going to have pictures, and they're going to say select a picture. So that it's really easy to cheat because you just type it in Desmos and pick the one that matches. I'm onto your games. And honestly, since this exam, well, on the exam, you're going to have the browser lock. But if this was in person, I would have a question like this, and I would have you graph it by hand. Anyway, so a lot of stuff. The takeaways for everything that we just did were know how to basically find x-intercepts, find vertical asymptotes, find horizontal asymptotes, and find holes. That's really the main idea. So if I give you any kind of rational function, a polynomial over a polynomial, know how to find those 4 things. All right, this last page is just 2 word problems, and they're not really bad. They're just try to scare you. So let's look at this. The cost C in thousands of dollars for a city to remove X% of a waste. So when they say X%, that means it's already a percentage. You don't have to convert or anything. So is given by this equation. Determine the cost to remove 20%, 40%, and 90% of the waste. So here, X is equal to percent waste, and C is equal to the cost to clean up. And this is going to be in thousands. All right. So for part A, what are they giving us? This is where I would ask the class, what is this? Well, these are percentages. So that means that these are X values. And so all they want you to do is plug in X values. So part A is just find C at 20, C at 40, and C at 90. And so you plug it in. 80 times 20 over 100 times 20. And you can use your calculator if you want. I won't get mad. Okay. So here, though, it's going to be 20. But if you want to do your work, just do 80 times 20. Now, when you divide, be sure that the 100 minus 20 is in parentheses. 20. Okay. A useful trick that you can use with your calculator is if you press second enter, it brings up the last thing you typed in, and I can just change those 2's to 4's because I'm lazy. Okay, so 53.33333. And then if I plug it through the same thing and change the 40 to a 90, I get 720. Remember that this is in thousands. Okay? So to write that as a sentence, it's to clean up 20% of the waste. It will cost $20,000. I'm going to put K for 20,000. Okay, so, and then again, I just repeat this. To clean up 40% of the waste, it will cost, and they said round to the nearest thousand, so 53,000. Okay, and then finally, to clean up 90% of the waste, it will cost 720,000. That's why it's not feasible if you're doing a cleanup project. Like imagine you're trying to clean the oceans of all the waste in the ocean. Um, the easiest things to get are the big pieces, and you can do a sweep and get most of the stuff, and that's cheap. But if you want to go and get all the little things and all the little tiny things floating everywhere, it takes a lot more effort, and the more effort it takes, the more expensive it gets. So to clean a little bit of the river, yeah, we can do that. To clean more of the river, it gets a little more expensive. To clean 90% of the river, to make it almost where it's almost perfect, that costs 720,000. The closer you get to 100%, the more it's going to cost. And in theory, you can never get to 100% because that's basically going through the river and picking up every impurity in the river. And that's pretty much impossible. All right, part B says if the city has $320,000 budget for the river cleanup, how much can be removed? Well, the budget, that's my Y value. So here, and notice that the 1,000 is part of it. So we're just going to take that 320. So for part B, they're telling us that 320 is equal to 80x over 100 minus x. I kind of like this because we're just back to doing basic math again. What scares people is that they see a word problem and they freeze and they shut down. Please don't shut down. So 320 and then two more zeros minus 320x equals 80x. I can add the 320 to the other side, and that gives me 400. So 32,000 equals 400x, and then I can divide by 400. So I have x is equal to, and then you bring up your calculator. My brain is completely off right now. 400, so 80. So if you have a $320,000 budget, you can clean up 80% of the river. And we make that a sentence. All right. And really, that's all the word problems are in this section. They're just read the word problem. Either you're going to plug in for x, or you're going to set it equal to a number and solve. They just have little fancy words here, like this one. A certain diet pill is designed to delay the administration of the active ingredient for several hours. The concentration of the active ingredient is given by, and then they give you the equation. No kidding. Use a graphing utility to graph the function. So here they just want you to see what it looks like. And so you would get your calculator and you would type in 3x Why am I doing this? Anyway, yeah, this is what you have. So I could just use Desmos though. So much better. Minus 20x plus 51. Remember, I put my denominator in parentheses. And so if I graph it, whoop, notice that there's a little blip. So I'm going to kind of zoom in on the blip. I don't care about the left side, because remember, t is time. For t hours after taking the pill. So I'm not interested on negative. So my window for the negative, so I can see the axis, I'm going to put -1 to 10. And for y, I don't care about that, so that's going to be -1. Let's make this 20 and see what happens. There we go. So here we have our function, right? So we did part A. What are the domain restrictions of the function? Okay, so for part B, they mean realistically, what must, in this case, t and c be? And what I mean by that is t is equal to time after taking the pill. So that means that t must be greater than 0. I guess equal to, because right when you take it. But so that's why we just did the right side. Now C is the concentration. In the bloodstream. And the concentration in the bloodstream, again, that has to be greater than 0. You can't have a negative concentration of something. It's either in there or it isn't. And if it isn't, it's 0. So that's what they mean by the domain. So the domain of the function is 0 to infinity. The range of the function is also 0 to infinity. Okay, so even though this equation, I can plug in pretty much any number I want. So mathematically, the domain would be everything, if you look at the picture. Mathematically, the domain's negative infinity to infinity, but realistically, in terms of the problem, the domain is 0 to infinity. All right, use the graph to approximate the maximum concentration. And so here they actually want us to use our calculator. So we go to part C. And so if you have your calculator out, it has special equations if you go to second and then trace. So let me write that here. And we're going to choose maximum. Okay, you pick a point to the left of the bump. You pick a point to the right of the bump. And then basically it's doing an algorithm. And so you want your algorithm to be, the guess means just put your cursor as close as you can to the top. And there you go. So use the graph to approximate the maximum concentration. So we have a maximum of x is equal to 5.05 and y is equal to 15.07. Okay. It seems like a lot for a concentration. Milligrams per liter. Okay. So anyway, The maximum concentration is, and we want the Y value. And they say round to the nearest milligram per liter, so 15 milligrams per liter. And then finally, what is the limiting concentration? Limiting concentration, that's what I was talking about, the range, D. The concentration cannot go below 0 milligrams per liter. Now, and if you have other word problems, whenever they say limiting concentration or limiting something, they're looking for the horizontal asymptote. Okay. Anyway, now you have everything to do, not just, so you're turning in lab 6 tomorrow. So you have all the information you need to do lab 7. I realize there's an exam, so I'm going to make lab 7 due next Thursday. But remember that everything on it is still going to be on the exam. I just want you to focus on studying though. All right, so again, I apologize for screwing up, not screwing up, but I apologize for the roughness of this lecture. But anyway, hope you have a good one, and let me know if you have any questions.